Okay, in this short video, we are going to go through the concept of person time in a little more hands-on way. So, in this image, this is kind of a false situation, right? Because it's not like you're going to sit out and draw every participant who you're following in your research study, but it should give you an idea of how we count person time and why we do it. So, in this figure, you'll see that we have a number of lines, and each row, I should say, represents a different person in our study, and it shows us the time that they were in our study. And two things you'll notice right off the bat. So at the beginning of the study, point 0, some people were in our study at the beginning, but others are coming on and being followed after the study already started. So there's movement into the population. You'll also notice at the end that it's not that we have data on every single person in our final year of follow-up in the study, that we've lost people over time. So this population is dynamic at both the front and the end. And this is the situation where counting person time at risk is really critically important, because we can't make an assumption that people have been in our study and we've been tracking them and they've been at risk this entire time. We essentially have incomplete data. It also allows us to be much more specific in knowing, okay, at what year did they get the disease, and thus they don't continue to be at risk after that time point. So what we're going to do here is actually just count up person time and do some really simple calculations. So we have 6 different rows of people in this study. So let's just go through and count how much person time each person contributed. So row number 1, this person was there for 1, 2, 3, 4, 5, 6.5 years. Person 2 was there in the study, and we tracked them for 0.5, 1.5, 2.5, 3.5 years. Person 3, 1.5 years. Person 4, 0.5, 1.5, 2.5, 3.5. Person 5, 0.5, 1.5, 2.5, 3.5. And person 6, 1, 2, 3, 4, 5.5 years. So what we can do is add up along those and see how much person time our study population contributed. Okay, carry the 3, 9, 12, 13, 16, 19, 24. Okay, so in this study, over 7 years, where we had 6 participants that we were tracking, our participants contributed 24 person years. And as you can see, some were with us for almost the whole time, some came on as the observation period had already started, and some left our study or left our at-risk population before the entire observation period ended. Okay, so we can actually now move on and calculate our incidence density, which the formula is number of new cases over our person time at risk. So what we need to do is calculate number of new cases. So we're going to look to these explanations of why people ended their time at risk. So we have one person who exited our study due to being diagnosed with Susser syndrome, which is what we're looking at in this case. Here, this person just was with us till the study end. This person died due to unrelated causes. This person died due to unrelated causes. This person stayed with us to the end, and this person exited due to our outcome. So we have 2 new cases of our outcome of interest divided by 24 person years. So that equals 0.833, or 8.3%, or, and this is the way I do actually want you to do it, 83 per 100 person years, which we could also then expand I'm sorry. Excuse me, per 1,000 person years, because because the answer is actually this. That's what was throwing me, guys. So the answer, 0.83, ends us up with 8.3%, also known as 83 per 1,000 person years. We could also write this as 83 per 1,000 persons per year. We could also, in theory, write it as 83 cases per one person per 1,000 years, but obviously people don't live for 1,000 years, so that would be a pretty false way of doing it. So anyway, our next video will discuss incidence density in more detail, but this hopefully gives you a picture of why we collect person years, that in these very dynamic populations, it's a huge assumption that people would remain at risk the entire time.